something I forgot to mention in the previous one. So I told you that there is an example of the quasi-Fuchsian group whose algebraic limit and geometric limit are different. To construct that, so I said we should use then twist and just iteration of then twist and take the limit in a space which I wrote H of S. So we should compare this example of another example. So instead of twisting, instead of twisting a neck, so we should pinch a neck. Then what would happen? So the twisting is then twist is something. So you cut the surface along some simple curve and twist by rotate the one side of the surface by 360 degrees, and then place them back. So another deformation of Riemann surface is just pinch this simple curve. So we consider such a deformation. So let so fix some point in a Teichmüller space M, and suppose Mn is obtained from M by pinching simple curve C to the length 1 over N. Okay. Well, the length should be hyperbolic length, or something called the extreme length, so anything would do. So maybe in this case we should consider hyperbolic length. Then what the limit of well, probably yeah, N. So we consider limit of this one in IISc. So this is algebraic limit, what I call algebraic limit. So limit in AH of S. Then what you get is quite similar, or in a sense quite the same as the one which we obtained from the twisting. So what you get is geometrically finite Kreinian group, where the convex core has some cusp here, but as a total, the convex core has finite volume. So that's the same as the case when we perform the iteration of then twists. What's different is geometric limit. So we consider, well, so let Gn be a group, and we suppose, so we just, so in AHS is, AH of S is something consisting of the equivalence classes of the representations, but we can take a representation representative of the equivalence classes so that it really converges to some representation corresponding to that. Then this group, this image of representation converges to some something, gamma, some Kreinian group gamma, which I, in a geometric topology. And as I said, HC, so gamma is gamma contains algebraic limit, which I used the symbol psi in the previous talk. The psi pi 1 over S as a subgroup. So the gamma is an extension of the algebraic limit in general. But in this case, in this example of pinching, actually gamma is equal to algebraic limit. So the algebraic and geometric limit are the same in this case. So if you twist, then what you get as a geometric limit is larger than algebraic limit. But if you pinch, then what you get is the same as what you get as a geometric limit is the same as algebraic limit. So the two deformations are quite different if we consider the geometric limit, even though they tend to the same point in algebraic limit. Okay, that's what I wanted to add. And also, in the previous talk, I defined geometrically finite Kleinian groups, but I didn't give any example of the geometrically infinite Kleinian group. So let me just show you one example, or two examples, or three examples of geometrically infinite groups. And at the same time, I would like to define something called ending lamination, which is a kind of invariant for geometrically infinite groups. So to construct an example of a geometrically infinite group, let me first define something called pseudo-Anosov map. It's a homeomorphism from, so throughout the talk, so as in the previous one, the S is a closed orientable surface of genus G greater than or equal to 2. So pseudo-Anosov map is something like this. So actually there is a classification of automorphisms of a closed surface and into three types. So the first type is something called periodic. So this is the start of the definition. So something called periodic if there exists and with a natural number greater than 0, such that the iteration of phi for the n times is homotopy or isotopic to the identity. So then phi is called periodic. So it's a definition up to isotopy or homotopy. And second type is something called reducible. Again, it's a definition up to isotopy. So phi is said to be reducible if there exists an essential simple closed curve. Well, by essential, I mean something which is not null homotopic. So there is an essential simple closed curve C, such that and the number, natural number n, such that phi to the n C is homotopic to C. And what's pseudo-Anosov? So the pseudo-Anosov is all the other cases. So if phi is neither 1 nor 2, then neither periodic nor reducible, then phi is said to be pseudo-Anosov. So it's a kind of generic situation. But actually, if phi is pseudo-Anosov, then it has some kind of geometric property. So that's what actually Thurston proved. So actually, this kind of the classification was probably obtained already by Nielsen, but this kind of the characterization of pseudo-Anosov. Well, there's something, some kind of characterization of the pseudo-Anosov also by Nielsen, but in this form, in this rigorous form, it was Thurston that gave such kind of definition. So, and if phi is pseudo Anosov, then there exists two major laminations. I will explain what they are. So major laminations, lambda, mu, and real number, alpha greater than 1, such that phi of lambda is isotopic to the alpha times lambda, and phi of mu is isotopic to alpha inverse times mu. Okay, let me explain what major laminations. So, so for convenience, let fix some hyperbolic metric on this. This definition doesn't depend on the hyperbolic structure essentially, but it's easier to just fix a hyperbolic structure to the definition. So let's fix some hyperbolic metric M. Well, maybe something. Well, I will just ignore that symbol, but just fix some hyperbolic metric on this. So let us regard S as a hyperbolic surface. And then geodesic lamination on S is a closed subset of S consisting of disjoint simple geodesics. So the simplest example we can think of is just a single closed geodesic. It's a geodesic lamination. But of course, there are many other kinds of examples. So if you draw, for instance, two simple closed curve and some simple geodesic, which is not compact, spiraling around these closed geodesics. The union of three leaves like that is also a geodesic lamination. But so it's just a geodesic lamination. I haven't defined the major yet. So the major lamination is a geodesic lamination with the transverse invariant measure. That means, so if you have a geodesic lamination, leaves of geodesic lamination like that, then for any arc transverse to that, you get some number, some real number, some non-negative, probably positive. Well, if it's disjoint from the leaf, then it's zero. So that it's a non-negative number. So you get a non-negative number for each arc transverse to leaves, and the value of that arc is invariant, even if you homotop that arc along leaves. So if you move this parallel to the leaves, then what you get as a number is the same. So that's what we call the transverse invariant measure. So then we can see that if you, for instance, in this case, if you just put the number there and regard it as a Dirac measure, then you get some transverse measure. So if you just count, so if an arc intersects this curve n times, then what you get is just n. So you can have such a kind of measure. And also, of course, we can just multiply the measure. If you just consider something like what is a good symbol for R, for example, then and if you just define that if the arc intersects that curve once, then you get the point R, you get this number R, then the R times the intersection time, intersection number is what you get as a measure. So that kind of thing is also a measure dimension. But in this example, in this case, you cannot define a measure here, because if you put the measure, Dirac measure there, then, because it's spiral around there, so the measure diverges around this point. So this type of leaf cannot be inside the support of the measure. So to define the transverse measure, you have to remove such a kind of the leaf from the support. So what you really have is either this kind of thing, this kind of closed geodesic, or something called exceptional minimal set. Exceptional minimal set is something, so you have a very complicated kind of leaf. So if you consider, if you cut the leaf along its transversal, then what you get is a contour set. So either this type or that type. So that's what you get in a measure derivation. So as you see, so every closed geodesic or even closed geodesic with some weight, some positive weight like that, is regarded as a measure dimension. And actually, what Thurston proved is that the space of this is the space of the simple closed curves, and the space of the simple closed curve times a positive number. This is a dense subset in here, so dense. So I haven't talked about the topology, but this MLS has a topology coming from the weak convergence of the measure. Okay. So here you have two measured lamination. Actually, these two measured lamination, neither of them has a compact leaf, simple closed geodesic as a leaf. So they are they have only exceptional minimal leaves. So let me draw a picture illustrating the situation there. So you have some measured lamination lambda and another measured lamination mu, and they are transverse to each other. And as you move these things by automorphism phi, one of them is mapped to its. So it's like the map shrinks this direction and expands it to this direction. So they move this here like that, and they move here these parts like that. So the rectangle here is mapped No, in the square here is mapped to a rectangle there. So you stretch one direction and you just shrink one direction. That's what you get. So that's the dynamics of pseudo-Anosov map. So what Thurston proved is, so except for these two special cases, a periodic and reducible case, the automorphism of closed surface has this kind of dynamics. Okay. Now, we'd like to use this pseudo-Anosov map to construct the quasi-Fuchsian groups. So instead of the den twist or the pinching, we just use the pseudo-Anosov map or iteration of pseudo-Anosov map. So what we're considering is something like this. So it's a QF of so which factor we are? So we are moving the second one. So the M and phi to the n. So it's a pullback of M by phi to the n. So, and again, because we fixed the first factor by Bayes' theorem, we know that it converges to some representation in AH of S. So they should converge to some psi in AH of S. So what kind of Kleinian group is it? So actually, this is geometrically infinite. So H3 over psi pi 1s is geometrically infinite. And well, if I draw the picture, then it's like this. So you have so this is a picture of convex core. You have a convex core which is which has a boundary below, like this. The boundary is something quite similar to this case. But this part disappears. So the convex core is the entire part above this. So this is something like that. So it's homeomorphic. Convex core is homeomorphic to S times 0 infinity. And it has infinite volume. So now, well, if so this kind, so you have two ends for this manifold. One is here, and the other is here. So this part is something similar to the geometrically finite case. So this kind of end is called the geometrically finite end. And this kind of end is called geometrically infinite. So for a geometrically infinite end, you can define its invariant called ending lamination. So it's something like this. So you have a convex core whose end goes to infinity here. Then that means however far away you go, there should be a closed geodesic nearby. So you have a closed geodesic like that. If not, the convex core should stop somewhere. So there should be some closed geodesic going to infinity. And because this manifold is homeomorphic, we know that this manifold is homeomorphic to S times R. Well, we need to prove that, but well, let me just omit that part. So there is a closure disk like that. So you project the closure disk down to this surface S. So because it's S times R, so you just project to the first factor, then you get some closed curve on S. So you have a sequence of closed geodesic going to the end, and by projecting it to S, you get the sequence of closed curve on S. And what you can show, actually this is Bonaon's argument, but you can show this CI converges to a measured lamination. Well, this is a bit subtle point, because in this case, well, we just consider the set of disjoint simple geodesics. So although this set, the simple closed curves or simple closed geodesics with weight is dense. In a setting that CI may have self-intersection. So we don't know if this CI is simple or not. But using some very sophisticated argument by Bonaon, we can show that the self-intersection disappears in the end, and as a limit, you get a measured lamination. That's what we have. Like, it's not a lambda; it's a mu. One of them. But yeah. So this one, mu. So it converges to some measured lamination, and that measured lamination coincides with the measured lamination which appeared here. So from Sardar, you get these two laminations, and one of them appears as a limit of closed geodesic, projection closed geodesics going to infinity. And actually, we can, using this property, we can prove that actually this is the case. Well, it's a kind of cheating, but if we assume something that the argument is true. So we consider the length of so this is the hyperbolic length of mu on the structure obtained by putting back the first hyperbolic structure by the iteration of phi, n-time iteration of phi. Then this is the same, because this is a pullback. This is the same as the length of the n times iteration of mu. Now, n times iteration of n. So if you apply phi to mu once, then what you get is alpha inverse. So if you iterate it n times, then what you get is alpha minus n mu. So this is just a scalar. So this is just a scale. So here the coefficient here just means the multiplication of the measure, transverse measure. So if you multiply the measure by alpha minus n, then the length is just alpha minus n. So this one doesn't depend on n, and alpha was greater than 1. So this goes to 0. Okay. Now, this is the length on the on the hyperbolic structure, on two-dimensional hyperbolic structure. But you can compare two-dimensional hyperbolic structure with three-dimensional hyperbolic structure. Actually, there is something called Bears, in probably the Sullivan, Epstein, Merden, which says the length here is comparable to the length inside manifold. So what you can say is you can see that this implies QF phi and M I N star M. So this is three-dimensional hyperbolic manifold. If you consider the length of mu inside this three manifold, then it also goes to 0. That means if you try to realize this measured lamination inside this limit manifold, then you cannot achieve it. So if you try to, for example, if you just draw the picture of mu here, so it has some geodesic curvature. So if you try to decrease the geodesic curvature so that it becomes geodesic, then it goes far and far away, and eventually it disappears. So that is equivalent to this condition, actually. So you cannot realize measured lamination, mu, then it means it is a limit like that. So such a thing is called the ending lamination. The lamination you cannot realize as a geodesic, and it is equivalent to saying that there is a sequence of closed geodesic converging to that and tending to the end. So that geometry which geometry infinite group have typically. So that was the first example of the geometrically infinite Kleinian groups. So instead of fixing the first coordinate like that, we now moved the both coordinate. So we consider QF of phi to the n. Should I go there? Maybe phi minus n m and phi to the n m. So we moved both coordinates now. And so there's no guarantee that this kind of sequence converges. But Thurston proved that this actually converges. That's called Thurston double limit theorem. And it converges to some Kleinian group. So in this case, there's nothing like this bottom surface. The limit is something like this. So the entire manifold is a convex core. There's no proper convex subset which is deformation network. So the entire manifold is a convex core. And you have two ends, both of which are geometrically infinite. And we can, so we have defined something called ending lamination. So for the ending lamination, you have ending lamination mu on this side and lambda in the other side. Okay. And actually, this example was constructed by Thurston to show that there is a hyperbolic structure on a surface bundle of a circle. So if you consider S times unit interval and paste one side to the other by x0, identifying x0 with phi x1, then you get some S bundle over S1. It's something called mapping torus. And actually, this manifold, this limit, oh, no. This, where is that? Oh, this manifold covers, so what you get is something M sub phi. So this manifold covers that. So this is a Z covering of this manifold. Okay, that was the second example where the convex core is an entire manifold. Now, the third example is something something between the geometrically finite case and this case. So instead of considering the pseudo-Anosov defined on S, we are going to consider pseudo-Anosov map defined on a subsurface. So we consider sigma, which is a subsurface of S. So we suppose that the boundary of this one is essential. So that means no component of boundary of sigma is contractible. So for example, we consider something like that. So the S is the genus 2 and sigma is genus 1 with one boundary. So I haven't defined the pseudo-Anosov map for surface with boundary, but we can define it in the same way as the closed case. And we consider phi. I already used anyway. So I'd like to stick to the symbols phi. So phi is a pseudo-Anosov map on sigma fixing boundary, and extend it to the entire surface by defining the phi on the complement to be the identity. So it just moves this part, and is very complicated way as a pseudo-Anosov, and fixes entirely this part, fixes pointwise this part. Now, again, we'd like to consider the iteration of this map and the corresponding quasi-Fuchsian groups. So QF, which factor I fix? So the first factor was fixed. So it's M pi to the NM. Well, by the way, I forgot to mention, but in these two cases, so this case and the double limit case, the geometric limit is the same as the algebraic limit. So this one is also geometric limit. And the double limit case, this one is also geometric limit. So there's no larger geometric limit in these two cases. But in this case, we have a larger geometric limit. So algebraic limit is something like that. So you have a geometrically finite end below, because we fix that. And this map fixes this part. Probably I should write it, sigma prime. So you have some geometrically finite end here, but it's split along this curve C. So C becomes a parabolic element, and it divides the manifold into two parts, this part and that part. Well, I mean, it divides the ends of the manifold into two parts. this part is geometrically finite, and this part is geometrically infinite. So you have the convex core extends to that part. So as an algebraic limit, you have such kind of manifold. And the corresponding geometric limit is something more complicated. So you have two geometrically finite ends. So this is the algebraic. So geometric limit for this is something like that. So you have two geometrically finite ends, both of which faces a surface S, a surface homeomorphic to S. And you have a middle part, and you have, as in the case of dentist, you have rank 2 cusp here. And the manifold is split along one of the parabolic elements. And you have geometric infinite end here, and you have another geometric infinite end here. So the picture is like that. So you have 1, 2, 3, 4 ends. And only this part lifts to the algebraic limit. So this upper part disappears in the algebraic limit. So the covering of this one along associated to the subgroup corresponding to this bottom surface is the algebraic limit. So that's the picture you have. Okay. So are they clear? It's okay. Any question up to here? Yes. Yes. So again, the ending lamination of this one is a stable lamination of this pseudo-Anderson map. Partial pseudo-Anderson map. So the pseudo-Anderson on sigma. Okay. Okay. Now, then let me just go on. Carry on the work. So now I'd like to talk about, so these are kind of the, actually, so I use the theorem which I stated the previous talk to show this. So the theorem was, let me recall, the theorem was that the length function from the space of measured lamination times AHS to R. This is for a lamination and phi, you just consider the length of lambda with respect to phi. So this kind of function is continuous. That's what I stated in the last talk. And here, well, I use, so I didn't mention it, but I use this, here, something like that. Okay. So this is a kind of continuous phenomenon in the title. So even if the geometric limit is different and the geometric limit is larger or something like that, the function like that is continuous throughout the deformation space H of S. Okay. Now, what I'd like to talk about next is something discontinuous. Oh, I don't need it. Okay. So we start from the something called limit set. Yeah. So for Kleinian group, without torsion, well, in our case, we are considering the group in AH of S, so they are torsion free. So the limit set is defined to be a closed subset of Riemann sphere, which is defined like that. So if there exists a non-identical element in G, which fixes X, then we consider the set of all such points and take the closure. Then it's called a limit set. So in the case when G is Fuchsian, the limit set is nothing but the one-point compactification of R. So in the quasi-Fuchsian case, so it is the image of this curve by quasi-conformal homeomorphism. It must be some Jordan curves because it's a homeomorphic image of this curve. But it's known that this is very non-differentiable kind of curve. It's a something like character. So, and in the well, I haven't given the names for the three geometrical infinite groups. The first one is called a totally degenerate B group, and the second one is called a doubly degenerate group, and this one is called a partially degenerate group. So we have the three kind of example: totally degenerate B group, double limit, a doubly degenerate, and partially degenerate. Okay, so in the totally degenerate case, so it's something like tree. It's something like R tree. So it's like tree, but well, it's not a tree in the real sense, but it's something like tree. So it's a degeneration of, it's a degenerated form of a Jordan curve. It's something like tree. And in a case of doubly degenerate, then the limit set is the entire Riemann sphere. This is very easy to show for this example. And in the partially degenerate group, well, I cannot draw it. It has some region like that, and so along something like tree, you have some closed curve like that, and it's very complicated. So this is partially. Now, a Cannon-Thurston map is a continuous map from this circle to the limit set. So so let me just we are concerning AH of S. So we just fix some Fuchsian element, Fuchsian representation. Maybe what again? I use the symbol phi many times in different meaning, but let me just use phi again. So phi is a Fuchsian. So it's contained in AH of S or the QFS, and you consider any element in AH of S. Then Cannon-Thurston map for this psi, the second one, is a continuous map from R, the one-point compactification of R, which is identified with a limit set of phi, because phi was Fuchsian, to the limit set of psi, with the condition of the equivariantness. So so for any gamma in the pi1 of S, and any point in one-point convex system R. So phi gamma x, the image of phi gamma x is equal to psi gamma fx. So the map is equivariant with respect to the action phi and psi. Then it's called Cannon-Thurston map. We don't know if it exists or not, but if such a map exists, then it's called Cannon-Thurston map. And by this condition, it's rather easy to show that if it exists, it must be unique. But we don't know yet if it exists or not in general. So in the case psi, when psi is quasi-Fuchsian, it's easy to show that so it's for psi the unique Cannon-Thurston map. So it's the Cannon-Thurston map. The Cannon-Thurston map exists. So it's easy. But in other cases, it's very difficult to show that such a map exists. So the first example for which the existence of Cannon-Thurston map was proved, except for the quasi-Fuchsian one, is the case of doubly degenerate groups. So for doubly degenerate example, that is obtained by the iteration of the pseudo-Anosov map on both sides. Cannon and Thurston show this is actually why it's called Cannon-Thurston map. So the Cannon and Thurston showed the existence of Cannon-Thurston map. So they show that there exists a continuous equivariant map from one-point compactification onto Riemann sphere. So it was known that there is a continuous surjection from circle to the sphere. That's piano curve. So this is again an example like a piano curve. It's a surjection, continuous surjection from the circle to the sphere, but it has a additional property that this equivariance. So this one is called group invariant piano curve. Actually, that was a part of the title of their paper. So it's something group invariant piano curve they obtained. So this is, but for special case of doubly degenerate. Well, even the doubly degenerate group in general, but a specific example obtained by iteration of pseudo-Anosov map. So for general case, it's Mahan's result. So Mahan MJ, he showed for any psi in AHS, Cannon-Thurston map exists. Now, I have 13 minutes, okay. It's a bit different from my watch, but anyway. So 19 minutes, okay. And now, as we define in the length function, now we consider function of two variables. So it's something I like to write by CT. So it's a map from, well, it's not exactly AHS, but an lift of AHS into the representation space. So it's before modding out by conjugacy. So times 1 point compactification of real numbers to Riemann sphere. So which is defined by this. So CT psi x is so let f psi be the Cannon-Thurston map for psi, which we know, or which we know the existence thanks to MJ's theorem. So then CT psi x is defined to be f psi x. So the image of this point x by the Cannon-Thurston map for psi. Okay. So then you get the function of two variables. Okay. So the natural question which arises here is that if CT is continuous or not. So the problem is CT continuous? Oh, this was first posed by Thurston, actually. The answer is simple in this case, it's no. So actually, Mahan and Caroline series gave such a criterion for the uniform convergence. So MJ series, they show that so you consider a sequence psi I converging to psi in a lift of HS, then CT and psi I. So we just put the psi I here and regard it as one variable function on R hat. And this function converges to psi, this function, uniformly, if and only if the convergence is also geometric. So geometric limit, if the geometric limit of phi I coincides with psi, then this function converges to that function uniformly. Otherwise, it doesn't converge uniformly. So the continuity of the two variable function doesn't hold. But maybe the continuity is two variable function is too much to expect. So we can just consider weaker continuity. So it's, for instance, the pointwise convergence. So the natural question, next natural question, how about pointwise convergence? So we fix some point x in R and consider phi I converging to psi in HS tilde. And we'd like to see if the phi ix converges to phi tt psi x or not. So that's the question. And again, MJ series, they showed if psi is geometrically finite, as in the example of the limit of the den twists or the pinching. So in the pinching case, it's geometric convergence also. That's so you have a uniform convergence. But in a twisting case, geometric limit is really larger than algebraic limit. So you don't have a uniform convergence. But the limit is geometrically finite. So it is within this assumption. Then pointwise convergence holds. Okay, and they also showed an example. There exists an example for which pointwise convergence fails to hold. And so in the remaining 10 minutes, I'd like to state and explain the theorem. So this is theorem, which is a joint work with Mahan and myself. So we have completely determined when pointwise convergence hold and when it doesn't hold. So there is now. Well, at the moment, I'm not going to describe the condition in details, but there is a criterion for the pointwise convergence. Both for the groups and the point x. So we haven't determined for what kind of sequence we have a point for which the pointwise convergence fails, and also at what point the pointwise convergence fails. So we have determined both the sequence and the point. So let me show you the typical example for which the pointwise convergence doesn't hold. So that's the case of the partial degenerate. So we just let me draw the same picture as before. So you have some partially degenerate Kleinian group. So for such Kleinian group, let me draw the picture of the lift of the curve C. So you have a curve C with in this case the separating simple closed curve on the genus 2 surface. So if you lift it to H2, you have infinitely many curves like that. Okay? And then, one of the lift, one of the component is the lift of that part, and the other, well, the one adjacent to that is the other component here. So on this component, we define the pseudo-Anosov map. So you have a stable lamination mu. So you can draw a picture of the lift of the stable lamination. Well, it's hard to write it, but you have a lift of mu plan. Yeah. It's better not to draw anything. Anyway, so it's you have a lift of mu here, and for this part, we fix the structure. Okay. Now the pointwise convergence fails in near this point. So you have a lift of C, and you have a lift of mu, and there is one component of mu for which the complement. So you have a complement of mu, and here, and if you lift it to the hyperbolic plane, what you get is a polygon with infinite vertices at the circle at infinity. And what we can show is that at vertices of this infinite polygon, the pointwise convergence fails. And actually, these kinds of the point, the only place where the pointwise convergence fails for this example. And for any example for which the pointwise, so that I haven't stated the condition precisely, but what is saying in the statement there is intuitively something like this. So if you have some n, you consider the geometric limit. So as in the case of partially degenerate n, suppose you have some partial geometric infinite n appearing there, and suppose you have another n up there which faces that geometric infinite n, and so you have an ending lamination here. And the ending lamination is something you cannot realize it as a geodesic in this part. But if you can realize it instead of here, you can realize it here, then if you can realize ending lamination in the other end facing it, then pointwise convergence fails. And the point for which the pointwise convergence fails is just these kind of points. That's what the criterion here means intuitively. So we have determined the condition for which the pointwise convergence fails. So except for this point, the map CT converges pointwise. So that's all for now. Okay, thank you very much.